Okay. Hi guys. Nice meeting you all. Unfortunately, as Lucas said, it was not planned for me to give this workshop, so I'm not in Berlin. But let's still make the best out of it, and hopefully I can show off some nice things about our tooling, and also we all have some fun here. So this workshop is structured that I will first give a little bit of a longer introduction. A little bit will go over my slides, and then there is a show off of some code. And you can find this code here in this GitHub repository. And if you want to play along, also want to execute it on your local machine, tamper a little bit with the code, I recommend that you clone it now because there's also a Docker image in there, and the Docker image takes a little bit of stuff to build. So you can build it while I'm giving the rest of the talk, and then we can go over the code together, and I can show off a little bit of the capabilities of our tooling. But now I'll start with the introduction, the long introduction to the topic. And what I want to show you here is how we can use our tooling to build a coSNARK-powered dapp based on NoirCon2. And with the concrete example that I'm showing off is shuffling a deck of cards using our coSNARK tooling. And I first want to motivate why we need a coSNARK to actually be shuffling of these cards. So let's assume we have two parties here, Alice and Bob, and they want to play some card game. If they are locally together, there is actually no issue. They can just shuffle the cards themselves, and the other party can see that they're actually doing a great job shuffling. But big problems come when we want to do this shuffling over the internet or even on a blockchain. And the main issue is just trust here. So Bob will here be saying, I don't trust you at all, Alice, so I will be doing the shuffling because you will cheat. And Alice will essentially be the same, I cannot trust you, Bob, so I will shuffle myself. So they won't get to an agreement here. A simple solution to that would be that they just ask a different party, in our case here this is Charlotte, please shuffle the deck of cards for us. But if you think about it, this also doesn't solve the problem because Charlotte actually prefer Alice and might shuffle the deck in such a way that Alice actually has advantage. Or Bob is a really sneaky guy and he knows that they're going to play poker and he will be like, Charlotte, if you shuffle in a way that I win, you get half of my earnings. So definitely there's a lot of trust issues here and it doesn't solve our problems. And when you continue thinking about it, with technologies like a private state that we have now on the edge infrastructure, you cannot resolve this problem here. But you can use MPC and coSNARK to actually solve this shuffling problem and create something that we call private shared state. But one step at a time, let's just start with an introduction on what the technology behind the MPC, how this actually works. So MPC, I'm usually bringing the specific type of MPC called secret sharing MPC. What we usually have here is that we have a set of multiple computing nodes. In our case, here on the slide, we have 3. And what the data holders do is that when they have some data, this is cat here on the top, when they want to put this into an MPC application, they seek to prepare this data to these MPC nodes. And what the secret shares are essentially random looking data, and each of the MPC parties gets one of these shares, and this share alone is completely random looking to them and doesn't leak any information about the data. But the parties as a collective can use their shares to compute functions on the private data. And the output of the function is again secret shares, which are completely looking, which do not leak any information about the intermediate results. And once the parties combine these shares together, they get the correct output of the computation. Here, the supercat here down there. So there are, MPC is a very big topic with tons of different protocols and tons of different techniques. And I just want to give you some ideas on how this secret sharing actually could look like. So here on the slides, we have 2 different examples. On the left, there is a so-called Shamir secret sharing. It's one of the oldest forms. This was already invented in 1979. And here is when I have a secret value. I want to build a polynomial, a random polynomial, and then encode this private data as the constant term of the polynomial. And the secret share that sent out to the computing part actually points on this polynomial. And we do this because this nice property that one point does not leak anything about the polynomial itself, also not on the data encoded in a constant term. You can still reconstruct the polynomial and thus also the data if you have enough points, so with Lagrange interpolation, for example. And polynomials have this very nice property that if you have the points, you can compute function on these points and you get points of valid new polynomials. So you can do computations on that. Another very common way to do this secret sharing is called additive secret sharing. And this is arguably one of the most simple things you can do. Let's say we have three computing parties. What we do is you sample two random values and fix a third value such that the sum is the original data. That is all you have to do. And every MPC party gets one of these three values now. They are obviously random, do not leak anything about the data, and reconstruction is also very simple because you can just compute the sum over it. And as we will see on the next slides, you can do computations with secret shares. So as an example, if you want to do addition, let's say have two secret shared values, x and y. So what you would have here is the computing part has the share x1 and y1, computing party 2 has the share x2 and y2, and the third party has x3 and y3. And you can see if you add together your shares, so as in computing party 1, I add x1 plus y1, then this is already a valid additive share of the desired result. Addition is actually very simple to do in MPC because you just with local, no need to communicate with other parties and everything is fine. And this extends to every linear function like adding a constant value, multiplying a secret share by a publicly known value, and so on. These are very simple to do in MPC and you just put something locally, no communication involved. Becomes more complicated with nonlinear functions like multiplying two secret shared values. And again, there are tons of different methods on how we do that. I will just mention two of them so you have a little bit of an idea on how you can put that in MPC. And one technique, this is very well known, also very old, is called Beaver technique.
Roman?
Yes?
We have a question.
Sorry for interrupting. Can you scroll back to the previous slide?
Yeah.
I have a skipped question. Who does the addition? Like, we assume that we have two counterparties, they have parts, but who does the addition? Like, who owns the result? And who does the
Lucas.
Yeah, I can because the mic is here. The question is who owns the result x plus y in the end?
Who executes the operation?
And first, who executes the operation x y plus y1 and x2 plus y2, and then who holds the sum x plus y.
Yeah, so the MPC parties agree on a circuit in the beginning that defines what they actually want to compute. So the addition is embedded in there. And then each party has the shares. So party 1 has x1 and y1. So party 1 will compute an addition. Party 2 will also do an addition. It will do x2 plus y2. Party 3 will also do an addition. It's x3 plus y3. And these are intermediate results then. And these are also secret shared. And so that the result of this operation is not yet known to anyone, only in a secret shared form. And once the full computation, let's say a Poseidon head, whatever, is done, it depends on what you actually want to compute. If the output will be known to everyone, it will be known to a specific party, it will be known, kept secret, but only a commitment to the output will be published. So this is fully up to whatever you want to compute.
So in the case where we have one of the parties to own the result, we send all the intermediate results to this party and it finishes the computation and owns the result, right?
Exactly.
Exactly.
Okay, or this party can be an on-chain entity, a smart contract, for example.
Exactly.
Okay.
Yes.
Then it would be basically public. If we roll the end result on chain, if it's not Aztec or some private chain, it will be as you would publish it to the world.
Okay, thank you. Let's explain it.
Good, then let's continue with the multiplication. So how Beaver string works is that you generate somehow these helper triples here, A, B, C, and these are in secret shared form. And how to generate this is a completely different topic. There are tons of sub-protocols for doing that, but it will be too much for this workshop. So let's just assume we have these helper pairs. So these are secret shared. Nobody knows the data. Only the MPC knows as a collective know A, B, C. And C has this extra condition that it's the result of the multiplication of A and B. So and if you have those, you can use this secret shared A and B to mask the inputs for the multiplication. So A plus X, and you compute B plus Y, and you publish those values. So you reconstruct them on all MPC nodes. You can do this because no one knows the real value A, they only have shares. No one knows the real value B, they also only have shares. So that the result, big A, also capital A and capital B, are completely random and do not leak anything about X and Y. And once you have done that, you can compute this formula on the bottom here, and it will give you the desired result of the multiplication. And so if you do the math, you will see that it checks out. But you can immediately see this has a disadvantage compared to the linear operations like in addition, because this step in the middle where you bubble capital B, this requires the computing parties to communicate with each other. So they want to get this value in clear, so they have to send their shares to the other parties. And it is a common thing that you will see in MPC for everything nonlinear, like multiplications, bigger protocols like bit decompositions, etc., etc. There you always have communication involved. And it's the main thing I want to tell you here with these beaver trips. There's another technique on how you can do multiplication, for example, and that is one that we tend to use a lot because it has a lot of advantages. And that is when you have additive sharing, you send your share to the next party. So each party has 2 out of the 3 shares. And what this allows you to do is compute this formula here. And this gives you a valid additive share of the multiplication result. So there is a very, very simple multiplication protocol. But again, what you need to do here is you need to send a share to the other party. So there is communication involved. And this is something you cannot get rid of in MPC for more advanced functions. You always have this communication in there. And this is also in practice a lot of the limitations that you have for MPC. It's a communication. All right, that was intro to MPC. I don't want to talk more about it right now, a bit too much for the group, but let's now see how we can use it to solve the shuffling problem. So first, you all are familiar with zero knowledge, and I want to quickly mention what the properties you get from a zero knowledge proof. And that is, as you all know, when you have a zero knowledge proof for a computation, you can prove that the computation was done correctly. And when you have this knowledge property, you can also do this while not leaking anything about the inputs of the computation, also about intermediate results. MPC, on the other hand, as we have seen, is not a tool where you can prove something. It is a tool where we actually do some computations. And the computation is done in a distributed fashion on multiple computing parties. And the nice thing about MPC is that, same as for zero knowledge, input and intermediate results stay private. So what we need to do at TACEO is combine zero knowledge with MPC, get the coSNARK, and the coSNARK gives you the best of both worlds. On one hand, you can compute on private data without leaking the inputs and intermediate results. You can also prove that the correct circuit was computed, and this all without leaking any inputs or intermediate values. So that is essentially why we do a coSNARK. So how can we now do a coSNARK to solve the shuffling problem? So here you can see now on the slides on the right side, these 3 PCs. These are standing for the MPC network. So in practice, each of these PCs is an MPC node that should be hosted by a different entity. For example, one is hosted by AdStack, one is hosted by TACEO, and maybe one is even hosted by you. And what Alice and Bob now do when to shuffle a deck is they sample a random value. So Alice samples R1, Bob samples R2, and the secret share is to the MPC network. The MPC network then computes a circuit that shuffles the deck and also creates a zero knowledge proof that they have used the inputs provided by Alice and Bob to do this shuffling here. And this solves the issue. So what we have now is a shuffled deck. It is ideally still secretly shared and managed by the MPC network, so that Alice and Bob do not know the shuffled deck, but they get this zero knowledge proof that everything was done correctly. And then in further in the future, they use this shuffled deck to give out cards to maybe other players, or also do this shuffling for some data on the blockchain, and use the shuffled deck to play a game on, let's say, on the blockchain. So this is pretty nice. So are we done already? Unfortunately, not really. We will mention this in some slides, what is still missing, but let's think what we have done right now. So we want to play a game of cards. We have shuffled the deck and created a deck that no one actually knows the order in. Only the MPC network as a collective knows the order of the deck. But no individual, not even a computing input of the MPC network does know the order of the deck. We can give out these cards to new players. This is really simple because you can just encrypt a new card in MPC and then attach a proof on it that the correct card was encrypted and send it to the recipient of the card. So, and we further think about it. What we did was not just composing state of Alice and Bob, but we essentially created a new private state that is not known to anyone and that is managed by the MPC network. So this is what we then call private shared state. This is a state that is not managed by just one single party or is known to anyone. It's an unknown state, but it's still usable in computations later on. But the issue that we have so far is that we have any input verification. So we'll talk in the next slide what the issue is, but it's essentially the same issue that we all have on a blockchain that just has shared state like Edstake. You need to somehow verify inputs. Because if you think about it, when I'm now this node provider on Edstake and Alice and Bob come to me, we have a shuffled deck, nobody knows the cards. Blockchain will be like, are you sure? Really? How can you verify that? And the issue is when the MPC network approves that they have shuffled the cards with random inputs, they just prove that some random input was used for the computation. So it could have just used a different input from a different party. So what you always have to do, this is the same for any shared state, also for Edstake, is that you have to bind that input data of the computation to some public commitments. So as you know, on Edstake, every private state that you own, it has a commitment on chain. And even with the coSNARK, you cannot get away with not having commitments. You need this commitment still. So that the proof needs to be there is a random data as an input where Alice also has the corresponding commitment on chain. And then everything works out nicely. Okay, so that is in general how we can use coSNARK to solve this problem. And in the future, we want to have that we integrate the coSNARKs on some private blockchains like Edstake. How we can do this right now is that we have written this coNoir tooling. We'll see then later with the code demo. And there you can write your code in Noir and create the so-called ultra-honk proof. And if you want to use this proof system to create private state on Edstake right now, you can use the standard verified proof command in the Edstake smart contract language, which will essentially verify the validity of a proof on chain. What is happening in the background is essentially a recursive verification of the proof to make it compatible with the proof system that they are currently using in the on-chain infrastructure, which is called client IBC. But with that command, you can interrupt the ultra-honk proof system also with the Edstake smart contract. In the future, what we would like to have is also have an MPC variant of the full client IBC proof system, but we are currently only starting investigating the feasibility of and now, if we want to interconnect our coSNARK tooling with ultra-honk, you have to do that with the left side here. So far about the introductions. Are there any questions so far? And then, other than that, we will jump directly into the demo, and I will go over how you can write some coSNARK code and do the coSNARK key for the shuffling here. Lucas, are there any questions in the audience?
Not that I see.
I how
Okay,
I wonder.
then
Yeah,
let's just complete.
I'm curious like how feasible it is to do coSNARK over the Aztec transaction because it's super complex.
Yeah. So the question was how feasible it is to do a coSNARK over the Aztec transaction. So you mean like a transaction like spending some money, sending some money?
Yeah, for them, yeah.
Exactly. I think that's like
Yeah.
what Roman, like if you go one slide back, like he alluded to with this client IWC, that's what we're currently working on. And yeah, you can give more.
Yeah, so we are currently investigating what we need to build for that to work. But in the end, we have seen so far, it will be definitely feasible to build a coSNARK on that. But the concrete performance, I cannot give you any numbers so far. For that, we are too far. But we would see that it's definitely will be feasible in the future.
So maybe to sum up, like it's a huge engineering effort, but we don't see any research that we have still to do, but like just a lot of research and even more research to get it performant. But
Yeah.
other than that, we couldn't find any like blocker then that it shouldn't work out like exactly the same like with UltraHonk.
Yes, exactly. Great, then let's continue. So one last slide before I go into code. And this is essentially the setup that we now will be simulating on our machine. So in the middle, what you can see, I don't know if you see my mouse. Lucas,
Yeah.
do you see the mouse?
Yeah.
Okay, you see the mouse. Good. In the middle, there is this MPC network. So in practice, I've said this should be, each node should be hosted on by a different entity on a different machine. For example, Aztec, let's say maybe you even. But in our demo right now, we will manage all of these MPC nodes on the same machine to just show that it is gonna work. What we then also have here on the left side, we have Alice, which is one of the input providers, and on the right side we have Bob, the other input provider. And the third thing that we have is a normal NOIR program that you at NoirCon all love. I also love it. And you can run the normal NOIR program and use this as an input for the computation. So we'll also show off the code where we do shuffling with NOIR. So this will be the third input. So that the workflow that we will do then is that Alice will use our tooling to secret share her input. And this will be the secret shares here. She does this locally on her machine and then sends each share to one of the computing parties. Bob essentially does the same, has the input, uses our tooling, creates secret shares, and sends one share to each of the computing parties. They then perform the MPC computation and also creating the coSNARK, and they can then output these resulting secret shares to the desired recipient. In our example, this will be essentially Charlie will be a blockchain which gets the zero knowledge proof and the commitment to the data, and they will keep the secret shares of the shuffle deck by themselves. But this is essentially what we will do with our tooling. And then to have this proof, you can either use our tooling to verify it or also the Barettenberg verifier that is coming standard in the Aztec infrastructure. So the proofs are compatible with each other. So in this workflow, we will now show in an example. So here I have this repository cloned. That I've shown off on the slides, and you can find here. Lucas, is it big enough or should I make it bigger?
It's fine. It's good.
It's fine? Okay. Okay, so then here you can also find a big read, which essentially describes what I will be telling you right now. And all the steps that are involved to run the example, but I will go over it. Anyways, so what you can also find here is the slides that I'm used for this small introduction here. And we have two folders in here, the Doppeldeutsche. So we want to shuffle a deck here in Berlin. So we use coin cards, the Doppeldeutsche cards. So here essentially is the full code in there that is that we will gonna be executing. And here in the Doppeldeutsch to do, this is essentially the same code, but the main functions are missing. So if you want to try out yourself, if you can write the main functions, so it's not that much lines of codes, but still you can try it out here. You can use this repository here. But I will now go over the full run example here. So the most important function is here this shuffle function. So let's go just into it. It gets as an input this unshuffled deck. So our deck here has now 32 cards, and each card is represented as a number from 0 to 31. And this shuffle function is the core of our computation, is what we want to compute. And this one, we implemented this shuffle based on a so-called Pythonic sorting network. So this is a normal sorting oblivious sorting network that can use to sort some stuff in MPC and CK as well. And how you can translate this to a shuffle network is by whenever you do a compare and swap, instead of comparing two elements, you just flip a random coin. So that is essentially the way on how to get from a sorting network to a shuffle network. So whenever we want to compare something, we don't compare, we just flip a coin whether we should actually swap two elements or not. In the end, it is a very, very simple way of doing shuffling in MPC and CK. So the randomness here comes from this shuffle randomness struct, and it is actually fed by the inputs from the two parties, so Alice random element and Bob's random element. And what we do here is essentially we hash them together, produce an output field element, and do a bit of decomposition, which gives us with the used field 254 bits. And these are the random coins that we then use to decide whether we want to swap or not. And so you see, whenever we call this coin function, the next bit is gonna be. So in our example, these 254 bits are already enough. If you need more, you will just have to hatch more here. But that is essentially the whole shuffling protocol. And now let's have a look at the main function here. And what you can see is that I actually split the main function to a main inner and which I call from main, and then there's an extra commit. And I eventually want to split these two functions because the main inner function has the computation that we actually want to do, like first verifying the commitments of the inputs and then shuffling the card deck here. Well, was that a question, Lucas?
No, it was me drinking a cola. That's what something. Sorry.
It's fine. So, and you can see this main function returns this shuffled deck. But this happening in NoIR, when you return something from the main function, then this becomes a public input to the proof. So we don't want to return this shuffled deck of cards from the main function. We actually just want to return a document to it. This will, as I said, be a public input to the proof, so it really needs to be published here. So, we just publish a commitment to the spec, and yeah.
What are the asserts that? What is the semantics of the asserts that resides in line 41 and 42? Like
Yes. So
there are public input.
I said in the beginning of in the introduction that we need to verify that the correct inputs were used in the computation. And usually what we have in a blockchain like CatStack is that on chain there are commitments to data. So that this player 1 randomness is only known to Alice, and this player 2 randomness is only known to Bob. And here the MPC setting, the MPC nodes only have secret shares to those. But what is known on chain is a commitment to these values. And whenever you do computation in private shared state, you need to verify that the inputs actually match the commitments on chain. So the commitment here, you can see it in the main function, are public inputs to our NoIR code. And what we do is we commit again to the real to the input, and we do assert that the output of this commitment matches the one that we get as an input to the function. So this binds the input that we actually get for the computation to the commitment of obtain. This assert here is a constraint in the zero knowledge proof. So if let's say I have the random value 5 and I have the commitment to that on chain, but I use the random value 6, then the zero knowledge proof will fail. So this gives us the public auditability of that the correct inputs were used.
I'm
And the same also goes for the out.
I'm still missing the point. The commitment that is supplied by a user from the outside, it is produced locally before you take the input from the side from one of the users and produce the share out of it, right?
It was the R1.
Yes, so the commitment is on chain, and when the user secret shares its input to the network, it also provides the commitment. But then the critical part is that since this is a public input here in the file, it is required for the verification of the proof. So whenever someone, let's say a smart contract, verifies the proof, it also needs to provide the commitment. And that gives the verifiability that the commitment was good. So if the user would provide another commitment as the input and the verifier, this should be the private state of the chain. So I use this commitment, and the user did use a wrong commitment, the proof will fail.
Okay, thank you.
And this is also the same on the out. As I said, we don't want to return the DAC because the DAC should stay secret, but we want to return the commitment to the DAC. And this will then be also public input to the verification. Okay, so the code is
One more question.
simple.
Just really
Yeah.
quick. Is there any reason to use Poseidon 2 permutation instead of just Poseidon?
Like if there's any reason to use Poseidon 2 because like Roman is likes Poseidon 2 more than Poseidon.
No, sorry.
Yeah, so
Poseidon 2 permutation instead of Poseidon 2.
as well.
Why permutation?
Okay.
I just don't know a permutation one.
Why are you using Poseidon 2
If there's
permutation,
any-
so the permutation instead of only Poseidon 2?
Yes, I'm a cryptographer, so I know what I do. I do not recommend others to use it. But yeah.
No,
I could have used just standard hash Poseidon as well. But the nice advantage why I use Poseidon 2 in the first place is that there is a black box function in Noir, and that speeds up the proof generator, but also the MPC computation. So that's the reason why I use Poseidon in general. Yeah, and the specific function, yeah, I tend to use the permutation itself because control over it. But yeah, you can use whatever you have as long as you produce a secure commit there. Also, in a replication, you would need randomness as well for the commitment, but I thought for this basis to produces much more inputs and outputs. Does this answer the question?
Yeah, thanks.
Okay, so what we have as inputs here, as I said, is the secret share from Alice, secret share from Bob, and also the commitment, and we produce another commitment. And this is, I can show this off right now. We go this repository, and this is just a normal Noir repository. So I can use execute, for example, and it executes this whole circuit. I can now go test, which executes the test that I have down here. And to get the circuits, I can use compile. And I actually need to compile it here because our also gets compiled circuit as an input. And this compiled circuit is now here in the target folder in there. And our tooling, which I show later, will automatically take this compiled from here. So for the remaining executions, so I have told you that we need to simulate now 3 parties on our laptop, and they need to run in parallel. This can get a little bit cumbersome. So we have written here a just file which takes care of doing this simultaneously. So you can see, for example, here for proof generation, we have 3 commands, and these commands actually is 1 command for each MPC node. And I will use this file now to do all of these executions here. So the inputs, the first input is from Alex, so it has the value 1 and the commitment, and the second is from Bob, which has the value 2 and also the commitment to this value. And so the first step that we have to do is that each party secret shares the inputs and sends them to the MPC network. So I just do this with the command just split input. And you can see here it gets executed twice, once for Alice and once for Bob. So Alice here shares the input and writes it into this file here. You can also see out secret shared inputs that the files are produced. And so that this input Alice dominant 0 shared indicates that this is the secret shared input that should go to party 0. The second file here should go to MPC party 1, and the third file indicates that it should go to the MPC party 3. The same for for Bob. And in a real setting, they now need to communicate these shares to the correct C party. In our settings, since we simulate everything locally, we just have everything there. And the next step, what we do is more of a convenience step. And that is since each MPC party now has 2 input files, we need to merge them into just one file for further computation. And that is just merge input. And that produced the files in here, which are the inputs of each party for the remaining steps of creating the coSNARK. So this is the input for party 0, the input file for party 1, and the input file for party 2. The next step is actually creating the NoirCon code, and this is so the next step is just computing the NoirCon code. I just need to come from the witness generation, run witness generation. So what we do here, executing the code in MPC to get the output shares. So, and this a little bit longer, only 1 second. And what this produced is here now in the witness folder, each party has a secret share of the full witness. And this witness is then the input to your knowledge generation. And this is the next step. We can run proof, and this generates ultra honks your knowledge proof MPC and puts the output here into proofs. And it also produces this public put file, like is also done in Rettenberg, which essentially has all the commitments in there that you also need to verify proof. So in the proof 0, proof 1, and proof 2, these are now all the same, and these are your knowledge proof of the computation done correctly. And you can now use either our tooling or the Rettenberg tooling to verify proofs. And I can show you that they will verify with our tooling. So first, we need to create the verification key. And then I can just run verify, and it will tell you that the proof was correct. This proves you actually publish it on chain, and everyone can actually verify that the correct commitments were used and that the correct computation was done. So this was essentially the show of our tooling. What I want to highlight again is that we have just normal NoirCon code, and with our tooling, you can actually execute that in MPC, get the MPC computation and this knowledge proof for our tooling directly. No need to modify anything else. And what you need to take care of in practice when you use our tooling for compatibility with the blockchains is that you always output commitments and verify in commitments. The rest then should be normal NoirCon code. So are there any questions from?
I have a question about this merging step, merging inputs. So maybe I missed it before in the whole setup, but how could you repeat maybe how MPC nodes kind of are they waiting for some both inputs from both users, or when maybe one input comes from one user, how this works kind of in a blockchain setup?
Yes, as in a blockchain setup, how it would be that it would be somewhere this MPC network, and then one user, if the user to tell the MPC network we want to engage in a computation. And then the net will wait for inputs for input. So Alice will provide the input, Bob will provide the input, and at some point all of them have the inputs, and then they just tell the network start with the computation, and the network will then deliver the result to the required parties here. So you could probably build also something like where the MPC network watches on chain where it should wait for inputs, and it should start in computation, but there will also, since only Alice knows her secret data, it is not on chain, there's only commitment on chain, there's always some step involved where Alice needs to secret share the data to the MPC network. So we cannot get away.
Yeah, thanks.
So if the computation and in the network will tamper with the data, the final coNoir on the resulting node will find it out, right?
Lucas, I cannot understand that well. Can you repeat this?
Yeah. So like if like some of the MPC nodes tamper with the computation, the final result like you will find out in the final result was the question.
Yeah, we'll find out, because the coSNARK will not verify.
How many nodes in the MPC network must be
Honest?
yeah, not honest to actually bypass the verification on coNoir, on the final coNoir?
Yeah, so what they never can do is produce a wrong result, because the will always fail. That is the same as if I would produce a proof by computation locally. That is totally the same. But if enough MPC nodes collude and exchange their shares, they can infringe privacy. That's what they can get. But they can never produce wrong zero knowledge proof. That is the same as without MPC.
Thank you.
I have another quick question about this shared inputs. Can you just quickly show in the code how big they are, the documents themselves?
So that the inputs, I can go in there. It should not be. They have. Is it listed here? Yes. So that you see that they are very small. The thing is, we use this additive secret sharing here, and what they share is essentially just one field element. And with additive secret sharing, each secret share is the same size as the original data. So this is very, very small. What is bigger is obviously the output of the MPC computation, the witness, the secret share witness, because this is the whole witness that you have as an input for the youth generation then. But the in general input to the computation is in this case very, very small.
Yeah, I have a question. So, do we have the flexibility of instead of secret sharing shares, we secret share encryptions of those shares? I mean, does that involve lots of engineering or so?
So you mean instead of secret sharing the data, we secret share ciphertext and then decrypt it in MPC or something like that?
No, we see. So the parties they send to each other encryptions of the shares or their inputs. So instead of
yeah, you can obviously put something like TLS on top of it if you just want to protect the transmission itself. That you can definitely do. And there's also, when we use the tooling in practice, we will always use TLS as an intermediary for communicating between the parties. So we are sending encryption of the shares, and the other party decrypts and has the share now in plain. It answers the question.
yeah, I see.
But maybe like what you're thinking about, like why would you encrypt the secret shares? Like what we're
Yeah, so like for example, use cases where you want to have like extra properties from the MPC, like robustness and like verifiable secret sharing. Basically, we want first to check the shares of the parties, and once we those checks go through, then we can open the shares to everyone. But first we need them to be encrypted. So we encrypt first, we do the checks, okay, the shares are correct, then yeah, the party is decrypt.
okay.
Yeah, you can definitely do something like that, and also produce a ciphertext, send it to the parties, and only secret share the key once the checks were done, and then they can decrypt the data also in MPC to directly get the shares. There are also MPC-friendly ciphers, like you have CK-friendly hash functions in there, and then you can use those for these example use cases. Yes.
Okay, thanks.
All right. If there are no more questions, then thank you for your attention. I hope you learned something. I hope you will use our tooling in the future. And thanks for having me.
Yeah, thank you, Ron.
Thanks.
For attending.